Every web component you build follows a strict trajectory. It is instantiated, injected into a larger architecture, rendered for the user, and eventually dismantled. In Lightning Web Components, or LWC, this trajectory is governed by a highly deterministic lifecycle. The framework manages this sequence, moving the component through specific, non-negotiable phases. You cannot execute logic arbitrarily. To build performant applications, you have to map your code to the exact phase where the framework expects it. To map out this sequence, we project the creation, insertion, rendering, and destruction of a component onto a vertical timeline. Each node on this timeline represents a rigid phase with strict constraints. The framework exposes these phases to developers as lifecycle hooks. Misplacing logic across these hooks causes immediate structural failures. Firing state changes at the wrong moment triggers infinite render loops, and failing to clean up resources guarantees memory accumulation that degrades browser performance. Mastering LWC requires architectural discipline. Custom logic must align perfectly with the framework's strict sequence. We begin at the exact moment a component instance is created in memory. This chart starts with the constructor hook, executing basic state initialization. The super method must be the absolute first statement here. You are completely locked out of the broader application state. You cannot access the document object model, and public at API properties remain undefined. The logic behind this restriction is structural. The component instance exists strictly in isolated memory. It has not yet attached to the web page itself. The constructor must act purely as a baseline setup environment, configuring local variables and preparing the component for its eventual insertion. Once the initial setup in memory is complete, the component is physically inserted into the browser's document object model. Moving down the diagram, we reach the connected callback hook, which fires precisely upon this insertion. The component is now live. This phase serves as the primary integration hub, where the component connects to external data and services. There are specific valid operations for this phase. This is the exact place to execute initial data fetch requests from your server and to attach standard event listeners to the component. It is also the designated hook to subscribe to Lightning Message Service, or LMS, channels to establish cross-component communication. The connected callback acts as an architectural bridge. It turns an isolated, inert block of memory into an active participant in the application environment. After insertion, the timeline shifts to the render cycle. This is where the framework computes the physical visual output of the component. Following the path down, we hit the render hook. The framework calls this function to determine which specific HTML template to paint to the screen. By overriding this hook, developers build dynamic, conditional rendering architectures, swapping entire templates based on component state. Directly beneath that is the rendered callback hook. This hook is distinct because it fires strictly after every single render phase. You use this space to interact with newly painted DOM elements or initialize external third-party libraries. This connection creates a highly volatile environment. Updating a reactive state property inside this post-render hook triggers a failure state. Modifying a reactive variable here forces the component to render again, firing the callback again, which updates the state again, creating a catastrophic infinite loop. Because this hook executes repeatedly, you must enforce a strict architectural solution. By wrapping your code in a Boolean guard variable, such as hasRendered, you ensure third-party initialization logic only executes on the very first pass, cleanly preventing the infinite loop. The render cycle does not tolerate careless state updates. You have to enforce these Boolean constraints to prevent cascading performance failures. Eventually, the component reaches the end of its active life and is removed from the DOM. This brings us to the bottom of the diagram and the disconnected callback hook. This hook exists for resource cleanup. Any timers, manual event listeners, or LMS subscriptions created during the insertion phase must be systematically cleared here. Ignoring this hook means orphaned listeners remain active in the browser's background. Over the course of a user session, these accumulate into severe memory leaks. Running parallel to this linear sequence is a dedicated safety mechanism, the error callback. Note that this function takes two arguments, the error itself and the stack trace. This hook operates laterally. It captures and intercepts errors propagating upward from any descendant child components. By catching child errors before they bubble up to the application level, you prevent silent application crashes and preserve the ability to render a user-friendly fallback interface. Proper teardown and systematic error handling mark the difference between a fragile prototype and a stable architecture. Looking at this complete flowchart, the lifecycle architecture reveals itself as a highly structured state machine. We categorize the top section as Zone 1, initialization and setup. This covers both the local memory constructor and the DOM integration hook. The middle section forms Zone 2, the render loop. This is the cyclical, visually driven core of the component, protected by Boolean guards. The bottom and lateral sections make up Zone 3, teardown and safety, covering physical disconnection and error boundaries. Successful LWC engineering is purely a matter of architectural discipline. Every operation, from initializing variables to fetching data, must be placed strictly within its designated, framework-approved zone. Respecting the deterministic nature of these lifecycle boundaries ensures component stability and prevents critical resource leaks as your applications scale.